Okay, this video we will show how to use the element stiffness matrix in global coordinate for solving the basics plane task system, as shown in this example. We have three elements. Okay, and the first element we define by this. Okay, for the first element is connect with the node number 1 and node number 2, and this is for the second element, and this is for the third element. Okay, for the truss problem, we normally solve the problem in global coordinate system. This is maybe more convenient than solve through the local coordinate. Okay, so according to this, we have to derive the element stiffness for each element in global coordinate. Okay, let's just before we start, we have to consider the angle of each element. Okay, if we set up the global coordinate like this is the global coordinate xy. If we consider the first element, for the first element, that is, we have the node 1 and 2. Okay, if we set up for all elements, we may set up the direction in local coordinate. We may set up the node number 1 as the starting point. That is mean that node number 1 represent node I for local, and node number 2 represent node J for local. Okay, so according to this, if we recall for the relationship of local and global coordinate, for the case of element number 1, we will see that the angle theta is become 90 degrees. Okay, so if we consider the second element, that is the starting node is node number 1, and the end node is node number 3. That is, node number 1 is equal to node I, and node number 3 is node J in local. Okay, so it's in local axis. This is in local axis. That is node x hat. This is x hat. Okay, so according to this, if we compare with the global coordinate xy, okay, so this case for the second element, the angle theta is become 45 degrees. Okay, and then if we consider the last element that we set up, the first node and the fourth node, the first node become node, the starting node, that is node I, and the fourth node is the last, the end node, that is node J. Okay, so we will see that the global, the local direction x hat is lying along the axis of node 1 to node 4, and for this case, the angle theta is become 0. Okay, so according to this, we can summarize the value of each element by the table like this. It's for element number 1 and number 2 and number 3. Element number 1, theta is equal to 90 degrees. Element number 2, theta equal to 45 degrees. And element number 3, theta equal to 0 degree. And after that, we finding the term that is have to determine for the element stiffness that we already know from previous clip video. Okay, we know that the stiffness matrix of bar element or truss element in global coordinate represented by this equation. So from this table, we determine every term that is composed of cosine and sine and cosine square and sine square, and also the multiplication between cosine and sine. Okay, after we have this value, we come back to the stiffness for each element. So according to this, we obtain the stiffness matrix in global coordinate for first element. This is for first element. Okay, we obtain like this, and do the same thing for the second element. For the second element, that we have to use theta equal to 45 degree and get the element stiffness for the second element. Okay, do the same thing. That is for the second element is composed of the displacement at node number 1 and node number 2 and node number 3. Okay, and node number 3 over here. Okay, so from this, do the same thing for last element, that is the element number 3, that is connecting with the node number 1 and node number 4. Okay, right now we have the element stiffness, all element stiffness in global coordinate already, and then after that we assembling. This is the assembling process. So we have to expand the matrix that is composed of 8 by 8 component. Okay, because we have 4 nodes. For each node we have 2 components, that is in x direction and in y direction. So according to this, we using the direct stiffness by adding term from the individual element stiffness matrix into their corresponding location in the total stiffness matrix like this. And after that, we simplify the value by factor out some value and determine it. Okay, we obtain the total stiffness matrix in global coordinate as shown in this slide. Okay, so then we can write the equation into this form, and after that we know that the displacement at node from boundary condition, we know that the displacement at node number 2, node number 3, and number 4 is r equal to 0. So according to this, we can cut off the second row to the 8th row, the 3rd row to the 8th row, and also 3rd column to 8th column. And after we apply boundary condition, we just have only this term, just only first and second row of the equation. So the equation is reduced from 8 equations to be just only 2 equations like this after we apply boundary condition. And then, because this is a homogeneous boundary condition, so we can doing something like this. We can cut off the row and the column. We know the boundary. Okay, but if the boundary condition is non-homogeneous boundary condition, we cannot do like this. We have to take care of the value of the boundary condition also. Okay, so according to this, according to this equation, we can solve for the displacement at node number 1 in x and y direction like this. Okay, so from this solution, if we would like to know the displacement in local coordinate for each element, we can do the same thing as we show in previous example. Okay, and if we would like to find the force, the stress, sorry, if we would like to find the force and the stress for this case, for this example, we determine just only the stress in each element. Okay, we follow the previous example. And we have the equation sigma equal to C prime D. Okay, so for this case, we can determine for the matrix C prime, and we know that the displacement for each element, we expand and include the displacement that we already know by solving the equation, by solving previous equation. And after that, we solve for the stress for each element, and then we obtain the stress in each element like this. We may verify the solution. That is, if we consider the force equilibrium at node number 1. Okay, so that means that the summation of force in global coordinate x and y should be 0. Okay, so according to this, if we consider summation fx, that is composed of the force in second member and the third member. Okay, this for the second member, that is the second element, that is the stress multiplied with the area, that is become force, and after that the projection into the x-axis, that is sine 45 degree, that is equal to square root 2 over 2, and is minus the term of the force inside the third element, that is 1035 psi multiplied with the area. Okay, so we obtain the summation of force in x direction equal to 0. And for the force in y direction also, we do the same thing. Okay, we obtain the summation of force in y direction is also 0. That means that the solution that we obtain is satisfy the equilibrium, and we make sure that the solution that we have is correct. Okay. Okay.